So I'd like to talk about scalable, inconsistency, robust information systems. And one of the things here that's new is scalable. And the answer to that is that if the system is sufficiently small, like the kind that we originally started off in mathematics, like Euclid's system or piano arithmetic, if it's sufficiently small, you can make it consistent. But if you're dealing with kind of things that Peter Neumann and I deal with, and the rest of you deal with, that certainly Oracle deals with, which is big, okay, then we have discovered you can't make it consistent. In fact, they discovered this fairly early in the game, right? And since they couldn't stand the sound of the word inconsistent, they had to invent a new bug, a new word, so that they could just feel better about themselves. So they call them bugs. And there are various other euphemisms that we have, glitches, etc., for these things. But the point is, once the system becomes big, okay, then if you talk to the manager or somebody in charge of one of these big software systems, it doesn't make any difference if it's a humongous relational database, if it's an operating system, if it's the Google, okay, they have lists of thousands of known consistencies and thousands more that they're sure that they haven't fixed. And it's a serious matter to decide whether or not to fix one. Because if you fix one, you'll probably create two more. So it's not trivial. There's a cost associated with attempting to fix one of these things. So that's where the scalability fits in here. So we have this definition, which I invite you to poke holes in viciously, of what it means to be inconsistently robust. And it says, inconsistency robustness is information system performance in the face of continually pervasive inconsistencies, a shift from the previously dominant paradigms of inconsistency denial, inconsistency elimination, attempting to sweep them under the rug.
So it presumably encompasses fault tolerance and generalizes it in some sense.
Right, yes. Maybe, right. So we're going to hold the discussion till later, but yes, it encompasses a lot. And it's intended to be two things, an observed phenomenon and a desired feature, i.e. we can go out and measure the inconsistency robustness of a system, like the US government, and how it does as an information system in terms of managing its finances, and see if it's inconsistency robust, maybe, maybe not. And maybe it's a desired feature, right? Like maybe our friends in China say, we do better. Okay, so that's where we are on that set of the equation. And we're dealing with a context, okay, it's been going on for a very, very long time, 150 years now, that information systems double in power every 2.5 years. And this has been going on back since we first started, when the Arabs first invented zero and started doing calculations manually, that we have this amazing phenomenon of increase. So in terms of this endeavor, we'd like to learn from our precursors. And we think that in 1956, there was a kind of precursor symposium to this one, a very famous one, that was organized by John McCarthy at Dartmouth. And it was the inception of the field of artificial intelligence. So what can we learn from that one? Well, we might be able to learn several things. One of them is branding. For example, they thought it wise to include artificial in the title of their field. And this has caused no end of problems over the years, okay? And as the field developed, there were issues of recruiting people in, and they began to develop issues about over-promising and over-claiming in the field. That basically some of the founders in the field, and these were very good guys, this was John McCarthy and Alan Newell, Herb Simon, right? Very, very, Claude Shannon, very, very good guys, right? And Marvin Minsky, right? Very good people. And for example, Marvin was my co-supervisor, so I had some skin in the game. But anyway, they thought that one of the things that developed was making these predictions. In 10 years, we will be able to do X. And then 10 years comes around and you haven't done X, and people notice. And so that's been an issue, I think, that needs to be learned from. Another issue in terms of recruitment is video. And the place where video comes in is I can think of at least 3 things. And here we're not only learning from the Dartmouth conference, but the whole phenomenon of what was going on. And for example, Jeff Rulifson participated as one of the maestros in the mother of all demos, which was this video production. Or is it the father of all demos? Who knows? Yes. Which was a video production that had a tremendous amount of impact. And also, Alan Kay made some videos, and so did Seymour Papert, having to do with teaching children how to program computers, which had, I think, a huge amount of impact on the field. And I think that this tendency toward video is becoming even more important, and that's why we've gone to the trouble of video recording, at least, the first half of the day of each one of these things, because that's, I think, the way now in this world in which you start to have some impact. Okay, maybe you can't convey as much information as you can in a printed page. On the other hand, you can attract people, and so it's an excellent kind of recruiting and education tool. So there's things to be learned from that. Then there's a question, I think, in terms of starting something or continuing something, a question of breadth. And one of the things that we know that was noticeably missing, okay, from that first set of people was any kind of insight into sociology and anthropology and social issues. It just wasn't present. And we can only, that's not necessarily criticism, we can only see that in retrospect, okay? But it's something to think about going forward as you're trying to do something. It's what kind of breadth do you have going forward? And then there was another issue, and that is diversity. And there weren't very many women at the Dartmouth conference, which is really unfortunate, okay? Because I think that, particularly as we start to get in these kinds of more social kinds of things, that the women bring certain strength to the party that the almost dead white males, okay, aren't as strong at. So, and they bring insights, and also, it's the tribe, okay? The guys get together and think it'd be a great idea to go and jump off that cliff, and then the women say, maybe not so fast. So that's an important thing. And then there's a question of other cultures. I mean, this early conference really was a monoculture. And here, our conference, I think, is suffering because we have some participation from Japan. But unfortunately, Francisco Berto, our colleague from England and Italy, who has a copy of the proceedings, we weren't able to raise the money for his travel funds to come here, so we're missing him. Similarly, a colleague down in Brazil who does very good work in this area was not able to raise the money. So I think that it's a fair thing to say that we're still lacking in this area of cultural diversity. So, here's a very nice slide due to Hans Moravec that sort of plots, okay, at least from 1900 up through 2000, on a log scale, this exponential growth in the power of computing, which is quite a phenomenon, and we expect it to continue for at least through my lifetime. And so, but it culminates up here with this guy, the human up here in the upper right-hand corner. And so here we have our human now. So that's as far as we get. And I think that was kind of the conception of the Dartmouth conference. And basically, individuals don't scale. So E.O. Wilson has a famous saying, one ant is no ant. And I think it's equally true that one human is no human, okay? So we have to figure out how to do scalability beyond that of making this, individual intelligence, whether we can do it or not. Even if we can do it, it's not going to be no ways sufficient. So we have this notion of orgs, which goes all the way back to Vannevar Bush and J.C.R. Licklider. And that is, the idea is that there's a new form of life coming to this planet. Okay, it's silicon plus carbon. It's the electronics plus the humans working together. And when we do this, we can begin to bring some insights, okay, from human experience about how to scale up these systems. And the thing that we know how to scale up is basically human organizations. And human organizations are fundamentally based on notions of authority and accountability, and they scale up to a very large size. And then you say, bureaucracy, we don't want to go there. But you think about it. We have to have some kind of computational model that we can explain to the funders, that we can explain to the programmers, that we can explain to the managers, that's intelligible to users. So it's got to be something in their experience that's scalable. Differential equations, right, just aren't going to cut it. Neither is the first order predicate calculus. So what realistic alternative do we have? So we scale up these organizations and we divide them up so that they can have scalability. So here we have the executive guy up the top, we have the sales department, the engineering department, the accountability, and that's basically, we then have hierarchical parallelism and also hierarchical concurrency, because basically accounting has to be able to talk to sales, sales has to be talked to engineering. You can't all go up to this guy at the top, the executive, even though they try, Steve tries, to run it all, he can't. He just doesn't have the computational capacity. Now, these organizations are inconsistent by design. They figured it out that we don't want to have everybody thinking the same. That's disaster. So, for example, we want to have the sales guys thinking differently than the engineering guys. And we want to have the sales guys thinking differently than the accounting guys. Because the sales guys are trying to maximize their commissions no matter what, and the accounting guys are trying to stay out of jail. So there's a separation of concerns here. There's an inconsistency between these. And then there's this famous saying from sociology, I don't even know who invented this, that where you sit is where you stand, okay? So if you sit in accounting, you will stand for accounting, etc. And so the thesis is that in these large-scale systems, allowing inconsistency is necessary for scalability. You can't get it any other way. It's necessary for pluralism, and unless you're going to try to wipe out dissent the way that Stalin did in the Politburo, you need dissent, you need open-mindedness, you need whistleblowers, we need minority rights, we need checks and balances, and we need separation of duties. And all of those require inconsistency. So inconsistency is the norm. So there's a famous example of this that everybody knows, I think, due to Andy Heller, called Catch-22. And he said, quote, "A person would be crazy to fly more missions and sane if he didn't, but if he was sane, he had to fly them. But if he flew them, he was crazy and didn't have to. But if he didn't want to, he was sane and had to." And this, in the context of that book and that movie, makes perfect sense, okay? Because here we are in the middle of this war, right? And we have all these guys. We've got these commanders running missions. We've got the shrinks off to the side trying to prevent something crazy from happening, right? And we have these flyers trying to stay alive. And in the midst of all this large system, you have to have rules. Here's the rules. So now, anybody who reads Dilbert knows that in our large-scale organizations, this kind of thing is pervasive. And we all know how to deal with it. We all know how to either submit to the system when it's appropriate, game the system to our advantage, and generally try to stay out of trouble. So that's the norm. Now, we want computers to understand all this so that they can become more helpful. And you say, good luck to you. But here we go, because if the computer doesn't know what the rules of the game are and what the basis of operations is, how is it going to be of any help to us? We're going to forever have the same dumb, stupid systems we have now. And it's becoming more and more frustrating as the systems keep scaling up. More and more power. Every 2.5 years it doubles. The poor users are going crazier and crazier. So, we formalize it. And we try to formalize it in a reasonable way. It says, well, look, if X is able to fly and X doesn't fly, then X is sane. Okay, if X is sane, then X is obligated to fly. If they're sane and obligated to fly, then they fly. Yossarian, poor of sap, is able to fly. Now, if you fly, then you're crazy. And if you're crazy, you're not obligated to fly. And if you're sane and you're not obligated to fly, then you don't fly. And our friend Yossarian, considering the cast of characters in this book, Yossarian is sane. Okay, so we also know, background knowledge, okay, that the moon is not able to fly an airplane. And furthermore, the moon is not obligated to fly an airplane. Therefore, we conclude that the moon flies an airplane by the rules of classical logic. You put this into your resolution theorem prover, and it says yes. Just terrific, right?
Which is different than fly me to the moon.
That's right, yes, that's right. So, what's to be done? Well, Wittgenstein said some very wise things about this 80 years ago already. He said, even at this stage, I predict a time when there will be mathematical investigations of calculi containing contradictions, and people will actually be proud of having emancipated themselves from consistency. Turing, okay. Turing comes to Wittgenstein's seminar, right? Young lad that he is. But he's not taking this lying down. Turing says, the real harm will not come unless there's an application, in which case a bridge may fall down, or something of that sort. You cannot be confident about applying your calculus until you know there are no hidden contradictions in it. Although you do not know the bridge will fall if there are no contradictions, it almost certainly there are contradictions, it will go wrong somewhere. And then Wittgenstein says something very important. He says, contradiction is harmless if it can be sealed off. But what prevents us from sealing it off? Nothing except 2 millennia tradition of logic, going back to Euclid, right? Mathematicians aren't going to give that up lightly, for sure. So what happens? Well, we run it through and we find the source of the problem. And the question is, what went wrong back here that we concluded that the moon can fly, right? Something went wrong. And what went wrong was there's an inconsistency. We can both prove that Yossarian flies and Yossarian doesn't fly. So now, Wittgenstein says, so what? Turing says it's a disaster, right? But Wittgenstein says, so what? But Wittgenstein doesn't have the technical chops, okay, to rework classical logic in a way to make a calculus that is inconsistency robust. But now, 80 years later, a group of us here at Stanford, Eric has helped participate in debugging this stuff, think that we've made some considerable progress on this. It's hard to know that we've got it absolutely nailed, okay? But we think that now we can reason about these things and have the inconsistencies sit there peacefully with each other. So that's nice. But there's another approach lurking around that's become more popular than the logic-based approach, namely this probabilistic approach. The probabilistic guys say, don't be so extreme. Why do you have to say that things either hold or they don't hold? Why can't we have a nice continuum of values in between, right? And have that solve the problem? Well, the great thing about formalizing things is the unreasonable power of mathematics, to quote Wigner. So we put that in, right? We send the guys out to sample the field, right? Anthropologists and sociologists, collecting statistics. And what do they say? Well, we sample things, and we say, well, we've sampled the guys able to fly, and the ones they're both able to fly and they don't fly, and guess what? Strongly correlated with being sane. And we've sampled the guys that are sane, and according to our sample, they're obligated to fly. And we put all that in. We put in the fact down here that Yossarian is able to fly with probability 1. And then we conclude from this the probability Yossarian flies is approximately 1. And the probability Yossarian flies is approximately 0, and we're in trouble. In fact, we're in even worse trouble than we were with logic, because we know how to contain the inconsistencies of P and not P, how to make them live together. We don't know how to make 1 equals 0 live at all. So we're in deeper trouble than we were before. Okay, so what the heck is going on around here? What we're doing is we're constructing circular information. And Anne-Marie Moll has studied this in the realm of clinical diagnosis. And she says, Moll shows that clinical diagnoses often depend on collective and statistically generated norms. What counts as normal hemoglobin level is a function of measurements of a whole population. She is saying then that individual diagnoses include connective norms, though they cannot be reduced to these. At the same time, however, collective norms depend on a sample of clinical measurements, which may be influenced by assumptions about the distribution of anemia, though it is, of course, not reducible to any individual measurement. The lesson is the individual is included in the collective, and the collective is included in the individual, but neither is reducible to the other. So what's going on is we're collecting this information, we're writing down these symbols, and we go through this whole process, and finally, when we get to the end, P meets not P. Because of these kinds of circularities in the information systems that resulted from the process of construction. So, what is reality? You say, well, I mean, that's medical stuff. Okay, what is the underlying physical reality here? Surely that can't result in inconsistent information. Well, we have our friend quantum mechanics, which is one of the fundamental legs of our physical understanding of the world. And Carlo Rovelli, I think, has developed our best understanding of that, and it's called relational physics or relational quantum mechanics. And they discard the notion of the absolute state of a system, the absolute value of physical quantities, or absolute events. Instead, state and physical quantities refer always to the interaction or the relation among multiple systems. Nevertheless, this is our best and most complete description of reality. So that's the physical basis for how we arrive at that. Basically, the physicists have become anthropologists. They say, you want to know what's going on. You follow around the electrons, you follow around the messages, you follow around the measurement systems, you see what they have to say to each other, and that's how interaction constructs reality. There is no godlike state view. It doesn't exist. And not only that, through some very clever experiments, they've shown that it is contrary to the physical measurements that they make that there would be such a thing. So, where that leaves us is the process of constructing information. Sometimes we like to fool ourselves into think that we're constructing knowledge, but that's knowledge is always provisional. What's indisputable is that we're constructing information. And this is by John Law, it says, the practice of fitting together these bits and pieces to produce more level, stable traces of information is a precarious business. Much of it goes wrong in practice. But when you're successful in making a package that sells to your colleagues, it's a wonderful thing. And the natural and social sciences surf on these provisional standardized packages that form part of or support these inscription devices, these instruments and practices. So the packaging is an important first step. And then these become routinized and start becoming mass-produced and spread around. And it's not so easy to once this happens, it's not so easy to overturn them. Once classical logic becomes routinized and established and taught everywhere and becomes the dogma of the land, it isn't so easy to overturn it. It comes at an immense cost. And there are people there bitterly resisting any change. For example, the censors on the Wikipedia don't want to hear a word of it. And they won't allow it in. Because the Wikipedia is supposed to deal with the conventional knowledge, right? The new stuff is not encyclopedic. So it's this way that scientific reality is produced that holds more or less. It appears to be independent of the particular us. And it appears to predate us, which it does. So this is how we create the thing called knowledge. It's routinized information systems. And this brings us to coherence without consistency. So Law says, we refuse the distinction between the literal and the metaphorical. We refuse the dualism between the real and the unreal, between the realities and the fictions. We work allegorically. We imagine coherence without consistency, and that's where we have to go for these large-scale systems, because we're not going to have any consistency. There's no way to test these large systems for inconsistency. Actually, there is. You deliver a copy of Microsoft Windows 8, and you ask me, is there an inconsistency? I say, yeah, I think that there are more than 5,000. I don't even have to look. I know the answer, right? Okay. So, let's go back to mathematics. And I'm almost done here, and we can have some discussion. Mathematics, ever since Euclid, has been in the business of inconsistency elimination. Division by 0 was quite troublesome, right? Because if you divide x by 0 and you get y, then y times 0 is equal to x. And if x is not 0, we're in big trouble. So you get rid of that one, right? Then the set of all ordinal numbers, okay? Also, paradox of set theory. The set of all sets that are not members of themselves, the famous one due to Russell, right? So mathematics got in the business of banning the monsters. They keep tightening up the rules, banning the monsters, getting rid of the monsters, right? We're going to preserve consistency. It was very successful. But then Gödel comes along and says, But what about the sentence, P is defined to be P is not provable? And you can actually construct this, it turns out, in terms of mathematics. Well, that one's got a problem. And it's not the problem that Gödel thought. Well, maybe we don't know what Gödel thought. It's not the one that Gödel said it was. And namely, he said incompleteness. Namely, he said we can show, we can prove that it's not the case that P is provable, and it's not the case that P is disprovable. We can't prove P and we can't prove not P. And this was against Hilbert, who had a program of eliminating the ignorabimus. The ignorabimus is the ignorance, the unknown thing. And Hilbert says, we're going to get rid of him. And Gödel produced a good one. But along comes Wittgenstein, and Wittgenstein says, incompleteness means inconsistency. And he has a little argument here. Okay. So, Gödel says, so here's his argument, right? And it's quite convincing. But it's just words, right? On the other hand, when Gödel proved his incompleteness theorem, he didn't do it formally. He also used just words. He says, well, we're not going to prove this in Russell's system, Principia Mathematica. We have to rise to the meta level to do our proof, right? But nevertheless, after he rose to the meta level, then he took another strategy. He went down to primitive recursive arithmetic and tried to prove it there. And then he said, Wittgenstein did not understand the first incompleteness theorem, or he pretended not to understand it, right? He interpreted it as a kind of logical paradox when in fact it is just the opposite. So here we have two ideologies, right? One, due to Kurt Gödel, which says that mathematics is based on truth, right? And there's no inconsistency. And there's a one based on Wittgenstein, okay, who doesn't have any truck with consistent, he doesn't care whether it's consistent or inconsistent, but he just happens to notice that incompleteness means inconsistency. And our task is to reduce it to mathematics so that it's ideology versus your lying eyes. And that's what we'll be talking about later on in this symposium, of what it actually, how does it actually come out when you do the mathematics in such a way that it looks like 2 + 2 = 4. Which side wins? And I'll bet you have a suspicion as to which way it works out. So, Rabelais says, with respect to things like that, is that we always have to be open to further argumentation. That a good scientist is never certain. And this certain means really certain. Lack of certainty is precisely what makes conclusions more reliable than the conclusions of those who are certain. Gödel was very certain. Because the good scientist will be ready to shift to a different point of view if better elements of evidence or novel arguments emerge. Therefore, certainty is not only something of no use, but is in fact damaging if we value reliability. On the other hand, the reality is that error is pervasive. So there was a famous talk that Doug Lennett gave at the AAAI one year that I went to. And his title was, with respect to psych, Mistakes Were Made. Okay? That's one stance. An alternative stance is, I was mistaken, and this is what I'm going to do about it. A very different stance. So looking at that, the question is, can we have integrity without consistency? And I like Madeline Griffin Heine's definition of integrity. Integrity is when what you say, what you do, what you think, and what you are all come from roughly the same place and are headed in roughly the same direction. So that brings us to our cloudy future, which is a double pun intended. Our cloudy future. So what is this business about the clouds, right? It's the data center reborn. And when I first came into computer science as a freshman at MIT, there was this humongous data center, right? With spinning tapes. It was the IBM 709, right? And it had operators, right? and they had the data center. And then it was replaced, okay, by the personal computer. There was the PDP-6. You sat there and you had it all to yourself. Personal computing was born. And then time sharing was invented. It was back to the data center, right? And then the PC came around. It was back to the personal computer. And right now these guys are dreaming back to the data center. It's all going to happen in the data center. But we should think about the economics of this. Where is it cheaper to do processing, storage, and communication? This thing is turning into a supercomputer. It's going to have many cores. Its basic only limitation is battery power, okay?
Data, actually, if you're talking about massive data.
Well, that's the, okay, right. So computation is cheaper here by far than the data center, just plain cheaper here. What about storage? So that's why it's in green. Storage is in yellow. So what do you do about storage? Okay, what can you do about storage, right? Well, you can cache things here. You can cache, maybe 10 years from now, a terabyte will be good enough cache, right? The rest of it, you keep encrypted back in the data center with your private key. Okay, so it's just as good as being here, because when the national security letter comes in to the data center provider and they say, okay, give me Jeff's stuff, they say, sure. However, if you want to read it, you got to talk to Jeff. Okay, so that's why storage is yellow. And then there's communications. Communications is the expensive part. You have to build cell towers all around the planet. That is really expensive, right? So here we sit, right? Computation's cheaper here. I'll be able to store anything I want to here, right? And to the data center, it's going to cost big bucks. So you think that maybe our cloudy future does not consist solely of clouds. In fact, it looks like they're kind of disadvantaged. But there's some larger issues too. I'm almost finished. There is the politics, i.e. privacy and security. What are we going to do about the next Nixon and the data centers? Because back in the Stone Age of Richard Nixon, to get to Ellsberg, he was the provider of the Pentagon Papers, to get to his psychiatric records, they had to burglarize the office of his psychiatrist. They actually did this. The next generation Nixon will just order it up from the data center, if that's where it is, right? So we got a problem. But we have another problem too. Namely, every administration, not just this one, is deathly afraid of being perceived as soft on terrorism. The unfortunate thing there is that if you find a terrorist act is committed, you find the smoking gun in the data center, then the hue and cry goes up. We have to prevent this. So the government says, sure, because they're desperate, right? They're being attacked by the other party for being weak on terrorism. We have a solution. We will vacuum the data centers and send the stuff to Fort Meade where it'll be properly analyzed. This is going to happen. Well, a little bit of it's happening now, but yeah, right, yes. But more of it's going to happen, okay. So you say, well, okay, so what? I'm not a terrorist. This is not going to affect me immediately, except the administration spokesman announces, well, we've loosened our requirements on national security letters. We issue maybe 10, 20,000 of them a year. It's no longer going to be necessary for an FBI agent, unwatched by any judge or anybody else, to have any kind of probable cause to go after Peter's bits. Because we got to catch the bad guys, right? The way to catch the bad guys is we got to be able to pressure the good guys to give us the information on the bad guys. So therefore, we need Peter's information too. Peter's a good guy. We admit that Peter's a good guy, but we still got to have his information. That was the official position taken. Makes sense in a weird kind of way. But it has another bad kind of side effect, okay? Which is what the Krupps discovered after they figured out that the Nazis maybe weren't their greatest friends in the world. Even though they let them charge any price they want and be a monopoly and have slave labor, it was still bad for business. Why? They no longer had freedom of action. They now had to get permission from the government to change things. Once the government is siphoning off all this information and sending it back to Fort Meade, you can't just change your system any way you want, because you'll break the surveillance system, which would endanger the country. So we have a real risk to innovation here once we get deeply into the surveillance society, that the companies are going to have a hard time innovating if they have to get permission from the government to change things. So, next to the last slide, possible next steps. What can we do? And we can talk about this during the seminar. Maybe we can have an NSF initiative in this kind of area. Who knows? They like sexy new things. All we have to do is buy the right clothes and show ourselves in Washington. NIH. NIH, they've got real problems. They've got big database problems, man, right? They've got an ontology effort here at Stanford. They've got inconsistent information to beat bananas, right? Okay. Industry, how do we get innovation? Through startups. We can try university industry collaborations, MediaX. Martha Russell is the new director here of MediaX, and she would like to have some industrial university collaboration. Computer science, we have a Mr. Privacy initiative here at Computer Science at Stanford, trying to get something going. So we can talk about these in the course of the workshop. Here's the schedule. I assume everybody's seen that, and I'll be happy to answer questions about it. And that is the end of my talk, and we'd like to now have a chance for people to have discussion about all these crazy issues that I have raised. Okay, Alan.
So half of your examples were inconsistency, and half of them were incomplete information. And I view those as completely different things. So, the catch-22 was clearly inconsistent, but the physics was a lot of it had to do with incomplete information or better information coming in later. So I'd like to clarify what you mean specifically by inconsistency.
Yeah, that's a very good point, and that is the classical point. And the answer, one of the answers there is that we have no way to detect incompleteness. We have no way to tell whether any given piece of information follows from what we have or not. And we have no way to test whether a given piece of body is inconsistent. So we don't have tests for either one in practice.
I had to
for big systems.
In my little 5-minute talk, I have a clip from Star Trek, and I had to shorten it to cut out the difference where the robot says insufficient information.
Right.
That's not inconsistent.
No. But to really know, and John McCarthy's done some work, to really know that you have insufficient information. Like often I think I have insufficient information, and Fania points out that I have the information, I just didn't access it. I mean, what am I, forgotten again? I mean, the erroneous unit strikes again. I mean, so it's really hard for me to know that I do not have sufficient information. That is an extremely hard problem.
But that's still not inconsistency?
No, it's still not inconsistency. But now let's go back to the physics situation. The physics situation is if you go into the details, is really quite interesting. You can have, in quantum systems that they've constructed these, have two observers see inconsistent things. And the inconsistency only gets resolved by their talking to each other. But their talking to each other changes the world. In other words, what you're always intervening on the world. In other words, the interaction creates the reality. The idea that there's a reality there, okay, before you start interacting with it, that's stable, is false. It's just empirically false, okay? It's the interactions that are creating the reality.
But the physicist would say it doesn't matter until you can communicate, because there's no operational thing you could do about the inconsistency, and as soon as you communicate, the inconsistency is resolved.
Now, technically speaking, the inconsistency doesn't exist until they communicate and they bring P and not P together. It's the God's eye view that thinks that there's an observer over here observing this and an observer over here observing that. That's not the way it is. Unless you're talking to those guys or they're talking to each other, it doesn't exist. Yes?
At one point in your slide, you put ideology versus your lying eyes.
Mm-hmm.
And I didn't quite understand what you meant by your lying eyes.
Ah, okay.
And how that's
Right.
on the other side of ideology.
Yeah, sorry, that was obscure. Okay. So, there's a famous paper by Wigner called The Unreasonable Effectiveness of Mathematics. And it all goes back to the Arabs when they invented zero. And the Romans said, there's no zero. You start counting apples with one, right? If there are no apples, you can't start counting. But nevertheless, the Arabs won because after they did it enough and they showed it to the Romans had to trust their lying eyes that yes, this zero really did exist and you could calculate it with it, okay, because they got shown, okay, zero in operation. So to settle this little dispute between Wittgenstein and Gödel, we have to find some kind of calculus that's convincing enough, like 2 + 2 = 4, so that one of them would have to cry uncle, saying, well, yeah, I guess I've got to trust my lying eyes. And it turns out Wittgenstein wins. That once you can write down this stuff, and we'll talk about this tomorrow morning. You can write down this stuff using these funny little turnstiles and these formulas. So it looks like, yes, it looks like Wittgenstein's got it.
So are you saying you should believe your lying eyes or you shouldn't believe your lying eyes? I'm not sure where you're putting.
Gödel will never believe his lying eyes. Ideologues, it's not a question of should. It's we're going to divide into several camps here. The ideologues, okay, the teabaggers are not going to change. No matter what the facts are, what their lying eyes say. Yes?
So it seems like you're lumping a lot of different phenomena under the label inconsistency, and maybe that's good. Maybe it's a good thing to treat them all as a unified thing, but it's also a little bit confusing. And I wondered if one of the things we might come out of this conference is like a taxonomy of different kinds of inconsistency. And I mean, there's at least two sort of major different kinds. One that there's things like database inconsistencies, where you just have two things that have different values for some variable, and then there's software bugs. Those are those are kind of different things, but we want to lump, but we're lumping them together. So I guess the question is that a sensible thing to do to try to tease out different aspects of it?
I think that's an excellent idea, and a taxonomy of inconsistencies would be terrific. And we should let Josh say a word, because he actually looks at this in his paper in terms of the evolution of inconsistent theories in physics and the things that come up. Do you?
Yeah, right. I hope I will be able to present this aspect during my talk. And we have isolated three main types so far. So the inconsistencies between theories when it comes to not seeing the whole thing you're measuring, and still measuring other aspects of the phenomenon that somehow point at these extra elements. And inconsistencies that arise when your theory is wrong with respect to the constants you're using. And the third one is redundancies as a form of inconsistency in physics. So if you have too many entities in your domain with respect, or too many names for the entities in your domain, this is a form of inconsistency as well, because you are measuring things twice, basically.
Edwina.
Yeah, one of the things that you haven't mentioned about organizations or systems or people is that they're always changing, and they learn, they adapt.
Right.
And so it's never static. And in fact, even going back to the earliest days of AI, I mean, not everyone was concerned about learning, but a few people were. And learning, I mean, Selfridge was, for instance.
Yes.
And with his models of pandemonium and things like that.
Right.
But I think it's very important.
And he was actually there at the Dartmouth conference.
Yes.
That's right,
yes, that's right. And so I mean, AI actually started a little before that, just wasn't called AI, right?
Yeah.
Okay. So, but anyway, the point is that none of these things are static. And if an organization is changing, we're changing. I mean, it depends. It's like you are tied up with the system. One part of the sales part of the organization might learn one thing. The lawyer part of the organization might learn something else. And that's going to change the balance, the interactions. It might introduce inconsistencies. It might resolve inconsistencies. But I think it's important to realize that none of these pictures are static. I mean, you've taken a snapshot, but they're always going to be changing.
Yes, that's a very good point. Yes.
So I'm trying to express the risk of an idea here, but I don't think we have really put our finger on what we're talking about yet. We're trying to get our arms around the failure of human ability to think about the world, and we're maybe not conscious enough of abstraction. And Mark will laugh because he knows I always bring this up. But you know, one physicist's answer to this is I think it's called the anti-realistic interpretation of physics. You know, electrons are not real. Electrons are just our best interpretation of the data we have today and a very nice model. And if we get some more interesting data tomorrow, well, the interpretation will change, but there is some reality that is the same. So where's the inconsistency there? And I think I can apply this. You talk about inconsistency in large systems, but us electrical engineers know that even the tiniest systems have a metastability problem. And so that's an inconsistency, because if you look at the systems that people build so far where they try to maintain consistency, the price they pay is waiting, which is where the performance comes in. So I don't think it's just large systems, and it's not just small systems. It's every system we look at, and therefore the notion of consistency is maybe just an artifact of distortions in human nervous systems, just like the blind spot illusion paints a false consistency where there's ignorance. So I have this funny feeling that there's something deep going on about understanding how my own thinking about things is limiting. And so I would be, I mean, taxonomies and breaking it down and formal stuff has its place, but for me it's just like these tiny pieces of the elephant. And what's going on for me is there's a deeper lesson about how human beings fail to think most effectively about things just because of the way we're constructed.
I think those are very good points. Now, one of our goals here is to try to get machines to understand these things. And machines are not machines are not great at metaphors and analogies. So, in terms of inconsistency from a machine's point of view, what you really want to do is you want to have P and not P sitting here in your hand, right? A particular P and a particular the particular piece. You got both P and not P, right? And so, okay, so in terms of that goal, right, both inconsistency denial and inconsistency elimination don't make any sense, because what lots of people try to do is they try to shy away from the inconsistency, right? They'll try to push it off, right? They'll do the he said, she said thing. There's no inconsistency, because she said P and he said not P. That's not inconsistent. So we're trying to avoid that maneuver, right? So the machine can actually see the P and the not P, right?
I have to interject because my goal is for the machine to produce value to people.
Uh-huh.
And that's very, very different place to start from.
Right. So that's a good objection. So now the question is, what possible value can there be in producing P and not P, right? Gödel says, let me out of here. I'd rather commit suicide, which he did, than go there. Okay, so now we have to look at P and not just P and not P, but the arguments in favor of P and the arguments in favor of not P. And then we got to look at the arguments against the arguments in favor of P and the arguments against, okay, the arguments in favor of not P. At that point, we call in our friends, the lawyers, and say, hey, look. And also, we call in any high-level manager, right? And what do they want? They want a range of options. They don't want P. They want both P and not P and the arguments favor and against. And then they want their underlings to debate them, right? So that some kind of reasonable decision can be made in the presence of inconsistent information. Yes?
I just want to point out, when you're talking about P and not P, you're acting, or we're almost assuming that these are nice, closed, well-defined predicates with no fuzziness or open texture or anything
Yes,
like that.
right.
And almost any predicate of interest,
Yep.
or at least outside of the field of mathematics, is going to have open texture problems.
That's
so,
right.
Whether Yossarian is sane or not
Yep.
is not an easy determination. And the logicians tend to, every
That's
P
right.
and Q is the same as every other. But
That's
I
right.
think we
Yeah.
have to respect that they're not all the same.
No, they're not. Yes.
I want to jump on your remark you made just a little while back that you want to avoid sort of he said, she said models.
Not to avoid them,
Okay.
but to pretend that there's no inconsistency.
Okay. Because that seems like a way to handle inconsistency. I mean, in some respects, to handle inconsistency, you have to have that. You have to have at least one piece of your system that maintains P and one part that maintains not P, and then somehow they have to interact to vote on it or something like that. But in some sense, you need to have separate loci of belief to do any of this stuff.
Uh-huh. Yeah, I'd like to give some of our wise men in the audience a chance to talk. Peter, what do you think?
I have a problem because I see situations in which P and not P are both wrong.
Okay.
The law of the excluded middle, in some sense, where the modeling is wrong.
Right.
And this seems to occur very often, where we're trying to prove something.
Yeah, you might be interested to know that in the logic that is inconsistency robust, the law of excluded middle does not hold.
I understand.
Yes, right.
I understand.
That's
I'm
not-
questioning
that's
the
right.
fundamental
Yes.
assumption that you're building all this up.
Right. Yeah. Right. So we'll talk about this some more tomorrow morning. Jeff, what do you think?
No, I'm with Dave more.
Yeah.
I need a few more hours.
Okay. Mark.
So, there's an old paper of yours that I think gets at the heart of many of these issues better than the notion of inconsistency. And that's the role of description and action in open systems. And the basic point that I took from that paper is that the operational, the procedural, what does one do, is in some sense more fundamental than the declarative, the descriptive, the issue of what is true. That I view the whole notion that we have beliefs and we're reasoning about things. Well, the reason why is because in evolving creatures that act successfully, it came to be an increase in fitness to have creatures that formed something like belief systems. So we came to have these things that we call belief systems about the world. But then, in introspecting, we came to reason about the belief systems. And these logical theories are just a first crude abstraction of what it is that evolved that we're calling belief systems. And it's a crude abstraction for exactly the reason you're now pointing out, which is these notions of logic have a fragility to them that the belief systems that evolved in our heads do not. In particular, this fragility in the face of inconsistency. it's not that we should be seeking to have P and not P in our logical systems at the same time. It's that we should be seeking to continue to be able to reason robustly in the presence of P and not P.
Right, exactly.
It's not that P and not P, it's good to have them. It's just that it's inevitable that you have them.
That's right.
And we observe in creatures that we think of as having beliefs that they're able to continue to act successfully in the world after they have contradictory notions in their head. So clearly, any account of that has to account for how to reason successfully in the sense of leading to successful action. Now, your notion of the manager doesn't want P or not P, he wants the range of options. That's not.
He wants both P and not P.
He wants both P and
And
not P.
furthermore, he wants his organization, if there's a lot of P around, if he's got any sense, so to speak, he's got any sense, he's going to have some guys out there seeking some not Ps as well. Because
But I agree with that completely. But the important thing there is that frame of thinking about what the manager wants and why. It's what he really wants is a range of possible actions, not so much a range of possible beliefs, right? The purpose is to have a range of possible actions.
And also, just one quick point here is that I don't think we necessarily want to try to reduce this whole thing to psychological belief of an individual, because we can ask ourselves, what does IBM believe? Not clear what IBM believes. How would you find out what IBM believes? Not so clear either, okay? So, and this has been the traditional thing, and the founders of the Dartmouth Conference were psychologists. Somehow, they left out the sociologists and the anthropologists, maybe to their detriment. Eh, Elihu?
Yes.
Yeah? Expand on that.
Well, it's hard to expand without going on forever.
That's right, yes.
People don't think one at a time. You can't think without having somebody to think with or against. Most of the, and moreover, most of the knowledge that we have is what at least some folks call common knowledge. It's not simply the belief that X is true, or the knowledge that X is true, but the fact that I know that you know that I know that we know it, right? So, and that knowledge about the fact that everybody knows that thing is the critical thing that makes the interaction, reliable interaction, possible. Once we have methods for dealing with that, we're going to be very confused. And I have to add on another one of my favorite sticky points. It's kind of hard to make arguments based on evolutionary theory when we're not sure about the validity and usefulness and reliability of evolutionary theory. We sort of get into a loop. So it's probably not a good idea to base arguments on that until we have it.
I could give a little bit, just a little bit. I want to finish up on this, and then we'll go to yours. I'd like to finish up with what Elihu was talking about, and that a little bit of my own intellectual history is that way back in the early 70s, right, we started networking together our computers, and we had this psychological AI cognitive model, right? The brain science and cognitive science and the task of constructing artificial intelligence were sort of all of the same mush. And then we networked the computers together, and occurred to me, and a good friend of mine, Victor Lesser, said, oh yes, let's have distributed artificial intelligence. We won't change our fundamental, model at all. It'll still be fundamentally a brain model, only now it will be a distributed brain. And I said, maybe this isn't going to work so well. At that point, I sort of fell in with Elihu Gerson and Susan Lee Starr and Anselm Strauss, right? Okay, and discovered there's a whole different way of thinking about this, just completely different. There's a reason why they're not all lumped in the psychology department, right? We have whole separate departments of sociology and anthropology. They just plain think about things very differently. And they are completely relevant to our problem. So that's been a traversal. And then they discover Bruno Latour And the way to understand science is not necessarily as to what goes on between a pair of ears, but in terms of a scientific community and in terms of a broader concern of the little shellfish that live in a bay outside France and how they're actors in a participation amongst other actors, that humans aren't the only actors rolling around here. And the way to understand science is, instead of just thinking in your office, sitting in your office and reading textbooks and imagining how they do their work, actually go out in the field and follow them around and see how science actually works, okay, is a whole different kettle of fish from psychology, the psychology of belief. And so we really need both of these perspectives and others as well. In particular, the one from our friends in law. The law guys have something to say? How you guys doing?
I'm taking it all in. I don't think I have ready yet.
Okay.
Same here.
Fair enough, no problem. I'd like to
I'll
get
say
other
one-
people who haven't had a chance to
I'll
speak.
say one thing
Yes.
about
Okay.
the legal side of things, even though there are lots of different task orientations. And when you're thinking of the law, just don't think of adjudication.
Mhm.
I mean, there's advocacy, there's advising, there's planning, I mean, there's administration. There are a lot of different things, and that means a lot of manipulations of P and not P, or the cases for and against. But it isn't coming out necessarily just a God's eye view. That's not the only task.
Right.
So.
Okay. Anybody else who hasn't had a chance to speak yet? Want to ask a question or make a comment? In that case, I think that we have two more on the table. Yes, Alan.
I think Markham hit the exact point.
Yeah.
It is the action in the face of consistency. Does Yossarian fly or not fly? It's one or the other,
Mhm.
right? And there is no way not to make a choice when faced with inconsistency. And I think that's the key issue here to me that we have to deal with.
Yes, action is extraordinarily important, and in fact, we can actually prove a technical result, okay, to the effect that logic is not a sufficient basis for action in these concurrent computer systems. You actually prove a theorem that there are computations that a Turing machine cannot do. There are concurrent computations a Turing machine just plain cannot do.
So to me, inconsistency robustness is the ability to make decisions, even in the face of these true inconsistencies.
Yep. So, Dan, what do you have to say?
Oh, I'll wait for a while.
Okay.
Oh, just a little
Yeah.
variation
Yeah.
on what
Right.
you just said.
Yeah.
It's not just, there's a certain kind of action which I think is also important, that is to make representations in the face of
Yes.
inconsistency. That's an action too,
Right.
because it might help me later. I might not want to act right now.
Right.
I might just want to store up a model
Right.
of something, and that's a very important thing.
And this is the whole business of speech acts, okay? What's making inferences is taking action, okay? And sending messages around through the system, okay, is taking action.
I just want
And it's not just about P and not P, it's about the orders and requests that you make and the permissions that you get. Yes?
just another small argument, and that is the psychologists, the brain theorists, know that when they open up a brain, it isn't just one thing going on in there,
Right, yeah.
and it isn't just one belief at the top of the hierarchy. There's a lot of different subsystems and a lot of different neurons, and things are going on a lot underneath. You open up a brain and you get another kind of sociology. So I wouldn't oppose those two as much as you do.
Right. But it may be that the sociology that goes on within the human brain is somewhat different than the sociology, for example, that goes on inside the Apple Computer Corporation. Or inside Oracle. Well, maybe not. That is an empirical question. That's
And
right.
maybe your actor model can model both.
Maybe, that's right. Yes. Okay, yes. Mike.
I just, wanted to make a sort of a intellectual connection between, so some of the stuff that Mark was saying about focusing on behavior, so that there was a movement in AI, 10 or 15 years ago to focus on behavior-based systems, at MIT. This was done by Rod Brooks and David Chapman and Phil Agre. So they made a number of models where they tried to defocus AI entirely from representing and focus it on action. One of the systems that Phil Agre did, I just was thinking of this just a couple of days ago because I was reading Hugo Mercier's paper on argumentation. So Phil Agre had a system where it was driving behavior by modeling running arguments in the head about what to do next in some kind of behavior-based context. Like to make breakfast, you have certain rules that are firing, time to fill up the coffee, time other rules to fill up the dishes. And he had a dialectical reasoning model. So I hadn't thought of this in 10 or 15 years, but it came up a couple of days ago, and I think that's an interesting point where some of the stuff I know you're going to talk about later starts to impact on AI and more formal reasoning systems. That's all.
Okay. Yes, Mark.
Yeah, I just also want to bring up a point that actually, the thing that got me started was another old paper review, by the way.
Oh, thank you.
Offices are open systems. Which, by the way, I can't endorse the particular examples there because they're too simple to make the point. I don't know what to do about it in paper-length treatment.
Right.
But to summarize the point that's made, as I see it, is that the underlying reality that we're thinking about is much, much more complicated than any of the thinking we can afford to do about it. So that what we do is we think about abstractions of it. In order to be able to think about it, we form abstractions. Different abstractions, an abstraction has to lose much of the details, so different abstractions lose different detail. And each logical theory where propositions are taken to correspond to something in the world is a proposition within some abstraction, and different abstractions have lost different details. And what we do is we cover reality with this little patchwork of micro-theories. And it's the propositions that are shared between two micro-theories where both of them sort of have them correspond to the same thing in the external world, but they're within different axiomatic systems. And that's where a lot of the need to reason across inconsistencies come from, is that in order to have a sufficiently precise treatment that you can have local consistency, it has to have a very small coverage. Seen in that light, the value of the kind of direct logic that you're now doing, the way I see it, is that by having a way to do formal reasoning where within one theory you can be more robust in the face of internal inconsistency, you can afford to have an individual patch in this quilt of micro-theories that has larger coverage because it can fit, we can have less certainty as to the consistency with which it fits the reality it's abstracting from.
Yeah, that's a very good point, and that kind of corresponds to the history of how it developed. Basically, but way back then, in sort of in the early 70s, with Planner and QA4, was we thought that we could have, these, and then Psych went and tried this for real. These little local theories that were consistent that would cover the world, okay, and it hasn't worked, okay. It hasn't worked because then you have to have correspondences between these theories, write them down. As soon as you do that, the inconsistencies come right back. And for any even small size theory, you can't test it for consistency. There is no practical way, and some people at Columbia have worked on this, and I've got some references in my paper. There's no practical way to test a theory for inconsistency. And if it might possibly be inconsistent, as we saw with Catch-22 producing that the moon's flying around in an airplane, okay, unless you can prove that it's consistent, you can't use classical logic. So I think that's the case, that certainly multiple theories is an extraordinarily important idea and correspondence rules between them, but you have to allow each one of them to be inconsistency robust. And by the way, the stuff that you talked about, offices or open systems, was actually work that I started doing for Jeff way back when he was at Xerox PARC, right? And he realized some of the problems that the Xerox was having in this area. And at Xerox, they actually had anthropologists, okay, like Lucy Suchman, and other people like that starting to go around and seeing what's actually happening with the people, as opposed to just having the nerds design more machines, whether they can be used or not.
So what does this mean for the usefulness of our theories if we can't even prove small theories to be consistent?
It means that that approach is a dead end, that you have to have inconsistency robust theories. You have to learn how to operate with them. You have to learn how to have P and not P, look at the arguments in favor of P and the arguments in favor of not P, and decide that the arguments in favor of not P are trash, which they sometimes are. Those are the easy cases, right? And in other cases, you can say, well, look, you know, if it's really so close between P and not P, let's just flip a coin. We got to make a decision. So let's do the break. Thank you very much.